I'll give you a warning when you use 10 of those minutes.
Yes. Okay. Thank you.
Okay. So now we have Weida, who's going to tell us about extended enriched gas and a multi-galaxy merger.
Thank you. You hear me? Yeah. So my talk today is about multi-galaxy merger Redshift 7. And here is my collaborators. We have Casey, Lou, Zixuan, and Edwin here. I would also like to take this opportunity to share with you my work in progress about using Lyman alpha transmission spectrum to study realization and to identify like the bubble. So I would like to start with the first project. In the last 4 days, we have heard a lot about clumpy galaxies. We have like coffee pot, bell cloud galaxies. We also present the correlation between the 32 and star forming clumps. The clumpy fraction also can tell us the assembly history of galaxies and also tell us the stage of the galaxy currently in. So I want to share with you a 5-galaxy merger with 17 star-forming clumps. It's quite dark here. We can zoom in and look in more details. On the top panel, it shows the false color image of 115, 150, and 200. And in the bottom, it shows the false color of 277, 356, and 444. So on the top, I use the orange circle to highlight the galaxies at similar redshift, and I use the dark purple label to indicate the foreground galaxies which should be removed. So these 5 galaxies, they all show very similar SEDs. 2 of them have spectroscopy redshift 6.7. The other 3, although we don't have spectroscopy redshift, we can say in the bluish band, which is the Lyman alpha drop. We can also say we can also see a flux excess here, which marks the emission oxygen 3 and H-beta emission line. So we perform the IC deflating to measure the photometric redshift. They all are the similar redshift as the 2 species. So we can pretty much sure they are at the same redshift, they are within the same structure. We can also see a diffuse green light around all these structures. This marks the O3 and H alpha emission line. So not all of these galaxies are connected by this diffuse O3 and H alpha line. We performed the automatic clump identification, and we discovered 17 clumps within this structure. This is a very large number. We usually expect only 2 to 4 star-forming clumps at high redshift galaxy systems. Here, this is the only one we identified with clumps, with more than 8 clumps in the Jade field at redshift 6.5 to 8. This system is also very rare in the simulations. Here we compare it with the Nikon catalog from the Santa Cruz simulation by Aaron. Nikon catalog is very good for this study because it collapses all the boxes along the line of sight into the projected plane. So it can enable us to perform direct comparison between the observation and simulation. We use the same method to identify JQ to identify JQ-like systems in this simulation, and we in 2 square degree we only identify 4 JQ-like systems. This tells us they will expect only like 0.1 such system in the Jade field. So this may tell us such intense galaxy merger with a lot of star-forming clumps will be underrepresented in the Nikon simulations. We performed IC fitting, we derived star formation rate and the mass. We found most of the clumps and galaxies within this system have very formation rate. One that's above the main sequence will Redshift 6. Interestingly, in the most massive one, we observe which have star formation rate consistent with this main sequence. This could tell us most of the future star formation will be consistent with XA2 star formation scenario. We can say the total star formation rate is also higher than the main sequence by 1x. Such a high star formation rate could rapidly grow JQ into a very massive galaxy. We could constrain how long would the galaxy sustain current by time analytical or empirical relations from literature. Mass of primary and secondary galaxies. We estimate emerging time scale to be 100 to 350 million years. If the galaxy grow following its trace and then stop its star formation, like by the AGN after the merging, so it could this trace will be very consistent with those with the star formation history of massive crescent galaxies we observed the redshift 4 to 5. So this provides us a very plausible evolution path to forming massive crescent galaxies. Those galaxies are thought to be cosmology challenger. Another interesting fact we observe in this system is the very diffuse OC3 and H-beta halo. Here, as you can see, the green light, which marks the O3 and H-beta emission line, this surrounding all the these four galaxies and even between these two. So this green light, this is especially this bridge. This bridge is only visible in the green. So it corresponds to the oxygen 3 and H-beta emission line. So this may suggest there is a metal-enriched gas bridge between these two galaxies. The question could be, how does the metal are deposited into this region? The galactic outflow has been frequently used to explain the, to eject metal-enriched interstellar medium out of the galaxy. But such large-scale outflow has already been seen in AGNs or quasars. It can hardly be seen in star-forming galaxies. We also performed a single-phase galactic wind model. This is done by Zixuan, which he did a really great job. We assumed the energy input rate and the mass input rate to be proportional to the star formation rate, and we test with a set of energy loading factor and mass loading factor. We found that the maximum luminosity oxygen 3 and H-beta luminosity produced by star formation is 5 times 10 to 39, which is a factor of 20 lower than what we observe in this bridge. So that means the outflow cannot be the dominant driver of this O3 and H-beta bridge between the two galaxies. Another possibility is the interaction. As you can see, with the two galaxies getting close and pass by, the tidal interaction between these two galaxies will strip the metal-enriched interstellar medium out of the galaxy and form a bridge between these two galaxies. This has been suggested to be the driver of the emission line between, emission line bridge in Stevens quintet. The IFU observation suggests the line emission in this bridge is dominated by the shock from the galaxy merger. So this location is exactly similar to what we observed in the JQ, which suggests the tidal interaction could be a very plausible explanation, but currently we don't have IFU observation of this structure, so we cannot conclusively diagnose the excitation mechanism in this bridge. Okay, so the second topic I want to share with you is about using Lambda alpha transmission spectrum to study IGM. So we have used quasar to study realization since 2 to 3 decades ago. Here in the bottom is the lowest redshift quasar, and the top is the highest redshift quasar, in 2006. As you can see in the lowest redshift one, we can see a lot of fuzzies blueward of the Lambda alpha break. As the increasing redshift, these fuzzies disappear. This told us the IGM transmission increases with the increase. IGM transmission decreases with the increasing redshift, and more photons blueward of Lambda alpha break is attenuated by the IGM. With the advent of the JWST, I want to draw your attention to that this technique now can be applied to single galaxies with JWST prisms observation. Here is the Lambda alpha break. As you can see, we can see clear transmitted spectrum blue world of Lambda alpha break, and we can even see the edge transition from Lambda alpha absorption to Lambda beta absorption. We can use IC deflating to predict its spectrum blueward to Lambda alpha and compare the observed spectrum to this predicted spectrum to estimate the IGM transmission. We perform this technique to 5 fields, 3 fields from Kapler's study and Kapler's program, and 2 fields from the J's. I want to escape all the details, and I want to show you a discovery of Lambda alpha transmission region as shown here. So the orange line here shows the predicted spectrum we could observe for this galaxy at redshift 6.3. However, clearly we can see a high transmission at redshift 5.8 to 6. It is higher than the prediction by a factor of 10. And the size of this, the path length of this transmission region is almost 100 mpc. We can estimate the optical depth from this from the transmitted spectrum, and we found its optical depth is much lower than what we observed in previous quasar studies or simulations. And this cannot be explained by IGM density fluctuation. So this may suggest us we are witnessing a highly outlier region at redshift 5.9. So this outlier region is associated with galaxy overdensity. On the right, I show the histogram of the redshift histogram of J's, Fresco, and Mu's surveys. As you can see, at redshift 5.8 to 6, in J's, we see a very high a large number of galaxies at this redshift range, higher than average by a factor of 4 to 5. In Fresco, although we don't see a higher number in this redshift range, but in their study, they also claim over density redshift 5.9. In Mu's LAE catalog, they also say high number density, 2 times higher than the average. So this suggests the Atlas bubble is associated with overdensity. Here, I use the green to plot the galaxy, the bubble members, and the red the background galaxies. We can also use the other background galaxies to probe the IgM transmission. And what we obtain is they also see a tentative transmitted spectrum here, which agree with this one. The last slide I want to show is the 9 alpha equivalent width of 9 alpha emitters in this bubble. The red line is the 9 alpha equivalent width of galaxies in bubble, and the dashed lines are those from the previous JWAB studies of galaxies redshift 6. They are much narrower than what we observed in this bubble, so this suggests, and the equivalent width distribution of this bubble is consistent with those in the post-realization universe. So this again suggests Atlas bubble in the J's field at redshift 5.9. I'll stop here and leave summary here, and I can take questions. Thank you.
Okay. Are there any very quick questions? We're tired and out of time, I suppose. Let me see one.
Sorry, what distribution?
When you see the distributions of like this large overdensity that you mentioned, this large bubble, when you see these kind of distributions of galaxies and a large ionized region, how do you know you're not looking down a filament that extends a large volume?
Looking down the filament? Do you mean the filament?
Yeah, like with some impact factor, right?
The filament would absorb the 9 alpha photons and show a 9 alpha like forest.
But that would just be the
DLA.
core of the filament, right? As you get away from it, you'll have an ionized region.
You mean the void of the IgM or gas? Sorry, I may misunderstand.
Yeah, maybe it's a silly question. I'm just thinking, when you look at a filament with some impact parameter, there's going to be some region around it that is ionized. I guess the core should absorb and you should see it.
Yeah, maybe we can talk later. I may misunderstand. Sorry.
Okay, great. Let's thank Weida again. I think we have a discussion session.